In the previous section, we benchmarked loop periods using the tick count express VI. By the end of this module, you will be able to describe data flow in FPGA. So now let's start lesson 6, executing code in a single cycle time loop. So here's an overview of this lesson. We'll first talk about how data flow works in FPGA. Then we're going to talk about how we can leverage something called a single cycle time loop to execute code within one clock cycle. Then we'll talk about using FPGA clocks, and then we'll talk about troubleshooting single cycle time loop errors and how to fix those. We'll talk about also optimizing code within a while loop, and lastly we'll talk about pipelining. Alright, so let's talk about data flow in FPGA. So there's going to be 3 components that we're going to talk about that are necessary to maintain data flow. And first we're going to talk about the corresponding logic function, then synchronization, and the enable chain. So if we're looking at this slide, we see that the LabVIEW code here is a NOT function, which corresponds to an inverter in the FPGA hardware. So that's the logic that we see on the top third of this image. Now let's take a look at the middle. In the middle, you'll see a synchronization register, and that guarantees that data is output only on rising edges of the clock. Now at the bottom, we see something called the enable chain. So the enable chain section, it includes additional synchronization registers that only output on the rising edge of the clock. Due to the enable chain overhead, each function takes a minimum of 1 clock cycle. So what is the enable chain doing? It's guaranteeing that the FPGA logic executes in the same order as it appears on the LabVIEW block diagram. In other words, it's kind of enforcing that data flow. So let's take a look at this slide and see how the enable chain affects it. So over here, we've got something that's reading a Boolean value from the host, and we also have a NOT function, and we're also outputting it to a digital line. So if we're taking a look at that, on the bottom you see how there's the enable chain. That enable chain is going to enforce data flow, but it's also going to make sure that each of those items that you see at the top takes 1 clock cycle. So if we look at that total block diagram, that's going to take 3 clock cycles at least. Okay, so let's continue this topic. So because of the data flow principles that we just talked about in FPGA, we know that each function or VI is going to take a minimum of at least 1 clock cycle. Okay, and that's because of that enable chain. Functions can run in parallel, so we kind of knew that already, but some functions are dependent on each other, right? So sometimes you have a string of functions, and those functions have to run in sequence. So let's say, for instance, you had 10 functions that happen one after the other. Well, in that case, that whole sequence is going to take at least 10 clock cycles, right? Because each function has a minimum of 1 clock cycle. The application can only run as quickly as the sum of items in a sequence, kind of what we just described. Another thing to make a note of is while loops have a 2 clock cycle overhead. So let's take a look at the execution of this while loop. So in this while loop, we see a sequence of things going on, and some of these things are happening in parallel, but some of these have some dependencies on each other. So if we kind of add this up, we see that this code will take about 10 clock cycles, and then also it's inside a while loop. So each iteration, we're going to get a 2-cycle overhead from that while loop. So this code is going to take 12 clock cycles to execute, which seems like a lot considering the functions that we see here. So one way we can optimize this is we can actually use a single cycle time loop, and that will convert this 12-cycle while loop into something that we see on the next slide. So here on this slide, we see that same code we saw in the while loop, which used to take 12 clock cycles, and now by putting it in a single cycle time loop, it's going to actually only take 1 clock cycle to execute all that code. Now the way that this is able to do that is a single cycle time loop removes the enabled chain, and that's what's going to allow all these functions to execute within 1 clock cycle. And we'll talk about that more in the next section. Now you can describe data flow in FPGA. Next, we will describe how all code in a single cycle time loop finishes executing within 1 tick of the FPGA clock. In the previous section, we described data flow in FPGA. By the end of this module, you will be able to describe how all code in a single cycle time loop finishes executing within 1 tick of the FPGA clock. Okay, so let's talk about single cycle time loops. So what happens is LabVIEW will automatically optimize code inside a single cycle time loop. And the way it does this is it removes enable chain registers from the code that's inside of a single cycle time loop. By doing this, we're going to get better speeds, and it's also going to consume less space on the FPGA. So all code in a single cycle time loop is going to finish executing within 1 tick of the specified FPGA clock. So that's a huge advantage that we've seen. We can turn a 12-cycle while loop, and by putting it inside a single cycle time loop, we're going to reduce that all the way down to 1 tick. So you can get some significant speed advantages here. So how do you create a single cycle time loop? So the way you would do this is you would go to your project, you would go to your FPGA target and go to a VI that is on your FPGA target. So you would open that up, go to the block diagram, and you would place down a time loop on the block diagram of your FPGA VI. And then from there, you would just put the code that you want to execute inside that particular single cycle time loop. So this slide shows a comparison again of a while loop versus a single cycle time loop. So if we look at the while loop on the left, the code inside there takes about 5 ticks, and also you add the 2-tick overhead of the while loop, so each iteration is going to be 7 ticks. If we look at the single cycle time loop on the right, we see that all of that code, which looks the same, except that it's inside a single cycle time loop, it's only going to take 1 tick. Okay, so you get some, it's going to be, you're saving 6 ticks by placing it inside a single cycle time loop, and it's going to be much faster. In this slide, let's talk about how a time loop behavior changes based on what target it's on. So if you place a time loop on a FPGA VI, it's going to execute as a single cycle time loop and have the behavior that we just described. And again, you can use this to optimize performance. You're going to have better resource utilization, and also you're going to have much faster speeds. Now, if you use a time loop and you place it on a RT target, for example, it would not execute like a single cycle time loop. It would just execute as a time loop. So one reason that you'd want to use a time loop on an RT target is you can specify priorities. You can use it to separate deterministic tasks from non-deterministic tasks. And this is stuff that you can learn about in the LabVIEW Real-Time 1 course, or if you look at LabVIEW Real-Time documentation. Okay, so let's take a look at exercise 6.1. And if you're able to at this point, then go ahead and do this exercise. For now, what I'm going to do is I'm going to demo a solution of this exercise. And in this particular exercise, we're going to compare while loop execution versus single cycle time loop execution and kind of compare benchmarks. Okay, so let's take a look at this exercise solution in LabVIEW. So in this exercise, we have a while loop and single cycle time loop benchmarking, and we're going to benchmark the same code, except one's going to be in a while loop and one's going to be in a single cycle time loop. So let's take a look at this VI. Let's go ahead and jump straight to the block diagram. Okay, so if we take a look at this block diagram, we've got the same code up here, except it's executing in a while loop. And that same code down here is going to execute inside a single cycle time loop. And we're going to do a benchmark. So notice that over here, we've got a tick count. And then at the end of all this, we're going to do another tick count. And we're going to do the same thing down here. So we're basically measuring the time it takes to execute this code and to execute this code. So what's going on? If we look here on the left-hand side, we've got 2 to the 10th power. And we're taking that number, and that's how many times we're executing this while loop. So this while loop is going to execute 2 to the 10th iterations. Okay? If we look down here, we're also going to execute this time loop, or the single cycle time loop, 2 to the 10th iterations. Okay? So after that, we've measured how long it takes for each of these to execute 2 to the 10th iterations. We get the total number of ticks for both. And then we're going to divide both of them to find out what the average number of ticks per loop iteration was. Okay? So that's what we get right over here. Okay? So we would expect that the while loop is going to take more ticks per iteration. And how many ticks do we think each iteration of that single cycle time loop is going to take? Well, by definition, a single cycle time loop is going to execute all in 1 tick. So we should see an average tick of 1 for the single cycle time loop. So let's go back to the front panel. And we've already compiled this. So I'm going to go ahead and, if we want, we can put some values here. So I'll just put 2, 2, 2, 2, 2, 2, 2, 2. Okay, and let's go ahead and run this. So this is running on the FPGA, and we've done that benchmark. Okay, so we've got our average value. So this is just the average value of this particular calculation. But what we're interested in is the benchmark values over here. So here for the while loop, we see that 2 to the 10th iterations took 7,169 ticks, and the average tick per iteration was going to be 7. Okay? If we look at our single cycle time loop, the average tick, like we thought it was going to be, is 1. Okay? So this benchmark just shows you and proves that the while loop is going to take a lot longer than the single cycle time loop in this case. Okay, let's do the discussion questions. So the first one, why does the code require more ticks in a while loop than in a single cycle time loop? So we talked about this earlier in this section. We're going to have to deal with the enable chain overhead, and also the while loop itself has a 2-cycle overhead. In a single cycle time loop, it's going to be optimized, right? And what's going to happen is all that code inside a single cycle time loop is going to execute within 1 clock tick. So what is the purpose of the decrement function on the right side of each sequence structure? So if we remember from the block diagram that we just saw, at the very end, there was a decrement function. And the purpose of that, this relates back to when we were talking about benchmarking and measuring time between events. That decrement function subtracts 1 from the result of the calculation to compensate for the execution time of the benchmarking code. Now you can describe how all code in a single cycle time loop finishes executing within 1 tick of the FPGA clock. Next, we will use FPGA clocks to determine the execution time of the individual VIs and functions on the FPGA VI block diagram. In the previous section, we described how all code in a single cycle time loop finishes executing within 1 tick of the FPGA clock. By the end of this module, you will be able to use FPGA clocks to determine the execution time of the individual VIs and functions on an FPGA VI block diagram. Okay, so let's talk about using FPGA clocks. So if we take a look at this code on the left, that code, if it's outside of a single cycle time loop, is going to require 5 clock ticks. Okay, so no matter what, that code will always require 5 clock ticks. However, how long does 1 clock tick take? So how many seconds is 1 clock tick? Well, if you look at the time of a clock tick, it equals 1 divided by the clock frequency. So the default FPGA clock frequency depends on the hardware. For example, for R series and for CRIO, the default clock frequency is 40 megahertz. So that's how you know if you're using something with a 40 megahertz default FPGA clock, the time for that is 1 divided by 40 megahertz, which equals 25 nanoseconds. So that would be the time of a clock tick. However, if you alter the clock frequencies, you'll also alter the execution speed of the FPGA code, because by altering the clock frequency, you're also altering the time of the clock tick. So FPGA clocks, they're going to determine the execution time of the individual VIs and functions on the FPGA VI block diagram. So in this section, we're going to talk about a couple different types of FPGA clocks. We're going to talk about base clocks, derived clocks, and also top-level clocks, and the purposes of each one. So here we have the FPGA base clock. Okay, so the FPGA base clock is the digital signal existing in hardware that you can use as a clock for an FPGA application. So FPGA targets have an onboard clock. As we see on this screenshot on the right-hand side, the FPGA base clock here is the 40 megahertz default onboard clock. Now from your base clock, you can create derived clocks. So let's say you needed to create a clock that wasn't 40 megahertz. Maybe you need something that's 80 megahertz or 200 megahertz or something like that. Well, you can right-click your base clock and then select New FPGA Derived Clock, and you can get some other frequencies that are derived from your default clock, but you can set them to other frequencies. Okay? And the purpose of creating these derived clocks is you can use them as clocks in different parts of your FPGA application. So this is what the derived clock configuration window looks like. So once you create a derived clock, you'll get this window, and you'll be able to set what you want that desired derived frequency to be. So if you look at the near the top of this window, you see a item for desired derived frequency. Here you can put something like 80, and then what you want to pay attention to is in the middle section, you'll see what the derived frequency actually ends up being. So in this case, we have a desired frequency of 80, and we are actually able to derive that exact frequency of 80. So sometimes it's not going to match up, and what this window in FPGA will do is it will try to get as close to your desired derived frequency as it can. And we'll take a look at this again later. Okay, so now let's talk about the top level clock. So the purpose of the FPGA top level clock is that it's going to be the clock that the FPGA VI uses outside of single cycle time loops. Okay, so this will control the execution rate of the code outside of single cycle time loops. For example, if it's in a while loop or if it's just off on the block diagram by itself. The default top level clock is going to be your onboard FPGA clock. So if we look at this project on the right, it's for an R series board. If you take a look at that and you don't change anything, the default top level clock is going to be that default 40 megahertz onboard clock that you see in the project. However, if you want to change this top level clock, you can right click your FPGA target and go to properties. So let's jump into LabVIEW and see what this looks like. Okay, so let's take a look at clocks in LabVIEW. So if we're here under our FPGA target, in this case we have an R series board, notice that our default clock is going to be our 40 megahertz onboard clock. However, let's say I wanted to create a derived clock. Let's say I needed a clock in my application to run at 80 megahertz. Well, I would select my default clock. I would right click it and then select new FPGA derived clock. And once I selected that, it's going to open this window. And notice here I'm able to get a derived frequency. So let's say I wanted a 100 megahertz clock. I would select that, and notice as I set that up, it'll say the derived frequency over here. So this is the actual derived configuration. So here I'm requesting 100 megahertz, and notice that the derived frequency, it was actually able to get 100 megahertz. Okay, and it does that by deriving it from my parent frequency here of 40 megahertz. Now let's say I try something like maybe 82. Notice that I'm trying to get 82. But based on the parent frequency and these multipliers and divisors, I'm not able to get exactly 82. However, it's going to try its best to get something close. So in this case, it would actually be a derived frequency of 82.666666667. Okay. So what I'm going to do right now is I'm just going to change this to 80. And notice that I can get exactly 80. And it's going to tell me the derived period that's associated with that. And I'm going to click OK. So notice now, if I go to my clock and I expand it, I have the 40 megahertz clock, but I also have a derived clock of 80 megahertz. Okay. The other thing I wanted to show you is how do you select your top level clock. So remember, the top level clock is the clock that everything outside of a single cycle time loop is going to run at. So by default, it's just going to be your default 40 megahertz. But if I wanted to change it, I can right click my FPGA target, go to properties. And over here, there's a category called top level clock. I'll select that. And notice by default, it's just using the 40 megahertz onboard clock. If I wanted to, I could actually tell my FPGA VI everything outside of single cycle time loops to run at 80 megahertz. However, this is not such a good idea. Usually, you want to keep it on 40 megahertz and or on the default 40 megahertz onboard clock. And we'll talk about that more in the next section. Okay, let's talk about changing the FPGA top level clock rate. So one thing to keep in mind is most LabVIEW FPGA functions are designed to compile successfully at clock rates of 40 megahertz. So this is why the default FPGA top level clock is just that default 40 megahertz clock. So not all FPGA VIs will successfully compile with faster clock rates. So for example, if I was to change that FPGA top level clock to like 80 megahertz, then I might expect that some of those FPGA VIs that the functions that I've used that formerly were able to successfully compile, some of them might not be able to compile anymore because those functions weren't necessarily designed to compile at clock rates of 80 megahertz. So if you set this up and you run a compile and there's parts of your FPGA VI that are requesting rates that are higher than it can support, the compile will fail and report the failure if the clock rate is too fast for the FPGA VI. So now let's talk about using FPGA clocks with single cycle time loops. So what you can do is you can configure a single cycle time loop to use a specific FPGA clock as its timing source. Okay, so what that's saying is if I have a time loop, the way that I would configure this is I would double click that input node and I would get that window that shows up here on this screenshot. Okay, so as I'm configuring it, I can actually select a timing source, and if I was to select that 80 megahertz derived clock there and clicked OK, then that means everything in that single cycle time loop would try to execute within one clock tick of an 80 megahertz clock. Okay, so an 80 megahertz clock is going to have a associated period of 12.5 nanoseconds. That means everything in that single cycle time loop needs to finish executing within 12.5 nanoseconds. Okay, so that's how you can determine and specify how fast you want a single cycle time loop to execute. If you don't specify a specific clock, the single cycle time loop will just use the default timing source of the top level clock. So again, all code inside a single cycle time loop must finish executing within one cycle of the selected timing source for that FPGA VI to compile successfully. So if we take a look at this bottom picture, we see that we have a single cycle time loop, and notice that on the left side that it's been configured to use a 80 megahertz clock. Okay, so that means all the code inside that time loop must be able to execute within one clock tick of that 80 megahertz clock. And if the code in there can't possibly execute that fast and finish executing within that one clock tick, you're going to get a failed compilation when you try to compile this VI. Okay, so let's summarize what we've talked about for these FPGA clocks. So one, we have our base clock, right? So that's going to be your digital signal existing in hardware that you can use as a clock for an FPGA application. So this is your default onboard 40 megahertz clock. Well, if you want to create other clocks besides that, you can create derived clocks, and these are created from your base clock, and you can create clock frequencies that are different. So for example, instead of just the 40 megahertz, you can create an 80 megahertz, 100 megahertz, and things like that. Okay, and you can use these derived clocks in other parts of your application, such as the timing for a single cycle time loop. And then lastly, we have our top level clock, and this is the clock that the FPGA VI uses outside of single cycle time loops. So most of the time, you just want to leave that top level clock as that default 40 megahertz onboard clock. Now you can use FPGA clocks to determine the execution time of the individual VIs and functions on the FPGA VI block diagram. Next, we will troubleshoot single cycle time loop errors. In the previous section, we used FPGA clocks to determine the execution time of the individual VIs and functions on the FPGA VI block diagram. By the end of this module, you will be able to troubleshoot single cycle time loop errors. Okay, so in this section, we're going to talk about how to troubleshoot single cycle time loop errors. So the single cycle time loop, the contents that are inside it, need to execute within a single clock period for it to work. So some things to keep in mind in light of this. So some VIs and functions can't be used in that loop at all, right? Because some VIs and functions are not going to be able to execute within a single clock period. For example, if you take a look at analog input and analog output, so most analog input and output hardware is going to take multiple clock ticks to be able to either read that analog input or output something to an analog output. So we saw earlier the 9211, it takes 70 milliseconds for the conversion rate. So because it takes that long and it won't be able to happen within a single clock period, those types of functions can't be inside the loop. Now, digital inputs and outputs, on the other hand, can usually execute within a single clock tick. So those you can put inside single cycle time loops. Also, you can't put nested loops in there, so you can't put a while loop in there, or for loop or time loop, because those are going to take multiple clock ticks. Also, a loop timer and wait express VIs, those are going to take longer than a single clock tick, right? So those won't work inside a single cycle time loop. Also, you have to think about other objects or functions that require more than one clock cycle to execute. For example, the divide function is a pretty heavy-duty function, and it's going to take more than one clock cycle to execute, so you won't be able to use that function or the quotient and remainder function. So you can put a for loop in a single cycle time loop if the for loop contains numeric, Boolean, or comparison operations and uses only auto-indexed tunnels. However, objects that generate or contain state, such as shift registers, feedback nodes, or VI calls, are not allowed in for loops within a single cycle time loop. So if you want a more detailed list of unsupported objects, you can go to the LabVIEW FPGA help and find a list of those there. So what we see on this slide is a code generation error window. This window is going to show you unsupported objects, and this will pop up when you first compile an FPGA VI. So when you first compile the FPGA VI, before it even gets to the compilation stage, it starts generating intermediate files. So while it's generating these intermediate files, it'll know right away if you put an unsupported object in there. Okay, so you'll be able to catch some of these mistakes very early on. So in this case, we tried to compile a VI, but while it was generating those intermediate files, it noticed that, oh, we've got some objects in the single cycle time loop that aren't supported. For example, you see the divide and also the FPGA IO node for an analog input. So if you were to double click one of those, it would bring you to the spot on your block diagram where you use that inside a single cycle time loop, and you can go ahead and correct it by removing it or replacing it with some other logic. So the single cycle time loop is limited by logic and routing delays in the FPGA circuitry. So for example, the code that you put inside your single cycle time loop, if the way that it's implemented on your FPGA, based on the logic and all the routing delays to connect that logic together, if all those functions are not going to be able to execute and all those delays are not going to be able to execute within a single clock tick, then that single cycle time loop is going to cause your compilation to fail. So if the total path propagation takes longer than 1 clock cycle, compilation fails. There's no way to predetermine the path length, so what you want to do is you just want to use best practices and try to reduce that path length before using your single cycle time loop. So you want to make sure your code inside a single cycle time loop is optimized and you're using best practices. So on the right hand side, you see a compilation status window that has failed. So if you take a look at that, notice that in the description there, the status says timing error, and also it says that the compilation failed due to timing violations. This is most likely because you have a single cycle time loop in there, and then you're telling it to execute at a speed, and all the code inside that single cycle time loop could not execute within a single clock tick. So in this slide, we see that same window that we saw in the last slide. Notice that if you have a timing violation, you can actually click this button called Investigate Timing Violation. If you select that button, it'll open up a dialog, and it'll show you what the exact timing violation was. So you can see the logic, routing, and total delay of each item. And one thing I want to show you real quick is if you look at that very top line, it's a little bit small, but you'll see that the requirement here is you needed that single cycle time loop, all the code in there, to execute within 12.49 nanoseconds. So we see that requirement on the first line. But if we look at the total delay of all the code inside there, we see that it's 27.47. Okay, so when we implemented our code on the FPGA, it took 27.47 nanoseconds, which is higher than the requirement of 12.49 nanoseconds that we set our single cycle time loop to. So because that delay was longer than the requirement, it's going to cause our compilation to fail. So this is a very useful window. You can look through those different elements inside that time loop, and you can see how long each delay took. And based on that, you can try to fix your single cycle time loop and just figure out how to optimize that code to actually make it fit inside your requirement. Or you can try to change a requirement to be something longer that would accommodate the amount of time it takes for your code to execute. So there's multiple ways of going about and fixing these timing errors. So based on that timing violation analysis window and the information you got from it, there's a couple things you can do to fix the timing violations. So one thing you can do is you can try to speed up the path by optimizing the code inside the single cycle time loop. So by optimizing the code in there, the code is going to take less time to execute, so maybe you can still fit it inside that single cycle time loop. Another thing you can do is you could select the slower clock for the single cycle time loop timing source. So if you select the slower clock for the single cycle time loop, then each clock tick is going to be a little bit longer. That way you can maybe accommodate some more time for your code to execute. Another way you can do this is you can speed up your path by moving some code out of the single cycle time loop. So maybe some of the slower code, you can remove it from your single cycle time loop and put it outside of it, and that way you're still able to optimize some of the code that you have in there to execute within a single clock tick. The other thing you can do is you can speed up your path by reducing its length even further by using a technique called pipelining, which we'll talk about later in this lesson. So on this slide, we see how we can also use the single cycle time loop to optimize sections of code. So for example, let's take a look at this while loop here. So on the while loop on the top, we see that we have an analog input node, and then we have some functions in there. So we have a multiplication, we have subtraction, and then after we've done some processing on it, we then send it out to an analog output node. So based on what we talked about before, we know that the analog I/O nodes cannot go inside a single cycle time loop because they take more than 1 clock tick. So what we can do instead is maybe we can try to optimize sections of code. So if we look at the bottom, we still have the FPGA I/O nodes for analog input and output, but we've made sure that those are not inside a single cycle time loop. And what we've done is we've taken this algorithm and we put the algorithm inside a single cycle time loop, so that algorithm, that section can all execute within a single clock cycle. So notice that the loop condition terminal inside the time loop, it has a true constant connected to it. So what that means is when we get to this single cycle time loop, it's going to execute the code in there once, and then it's going to exit, and then it's going to go on to the rest of your code. So this is a handy way of optimizing sections of code and making them execute within one clock cycle. Okay, so at this time, if you're able to, it's a great time to be able to do exercise 6.2, and in this exercise, we'll walk through fixing a couple of these single cycle time loop errors that we've just talked about. For now, I'm going to do a walkthrough of this exercise for you to follow along with. Okay, so let's step through this exercise, and we will take a look at some single cycle time loop errors and troubleshoot them. Okay, so here we've got our FPGA target. I'm going to go ahead and open up Investigate SCTL Errors. And let's look at the block diagram. Okay. So looking at the block diagram, do we see any problems right now with this single cycle time loop? Well, I see two of them right away. So one of them is this analog input I/O node. So remember, analog input I/O nodes will take much longer than one clock tick. So because it takes longer than one clock tick, it's not going to work inside a single cycle time loop. Also, we see a divide function. So remember, divide is a very large function, and it actually takes more than one clock cycle to execute. So this also will not be supported inside a single cycle time loop. So just to see what would happen, let's go ahead and try to compile it anyways. So I'm going to hit run, and I'm going to try to compile it. So now it's generating intermediate files. And during that process, so before it even tries to compile it, when it tries to generate these intermediate files, it'll find out whether there are any unsupported objects inside your single cycle time loop. So notice that, one, we've got divide. So if I double click this, it'll bring me to the divide. So it's showing me that this is unsupported. And then also, if I click on FPGA I/O node, it'll also tell me the details that this object takes more than one clock cycle to execute. I can also click on Show Error, and it will show me where it is. Okay, so the way that I would fix this is I would move this outside of the single cycle time loop, and I would replace this divide function with something that's that does the same thing but is not as large. So I would replace that with a scale by power of 2, because I've got a division by 4. That's the same thing as scaling it to a power of 2 of -2. So I'm going to close this VI. I'm going to close this box and close this, and I'm going to go to a version of this where I fixed that error. So I'm going to open this up. Let's go to the block diagram. And now notice that here I have moved this outside of the single cycle time loop, and I've also replaced the divide with a -2 here. And I'm optimizing this part of the code by doing a true to the loop condition. Okay. So next thing I'm going to do is let me double click this time loop and set the clock rate that I want it to execute at. So in this particular project, we've got our default 40 megahertz, but I've also created a 80 megahertz derived clock and also a 200 megahertz derived clock. Okay. So right now I'm going to go ahead and select this 200 megahertz derived clock and try to compile this single cycle time loop at a 200 megahertz clock, which is very, very fast. So I'm going to click OK. And then I'm going to hit run and try to compile this. Okay, so most likely I'm just going to tell you now that this is going to fail because 200 megahertz is very quickly is a very fast clock, and most likely this functionality will not be able to fit inside there. So let's see what happens when we try to compile this. So let me go ahead and save some changes, compile it. And now let's see what happens. Okay, so we've done this compilation, and now we see that the compilation has failed, and we notice that the status here is a timing error. So if there's a timing error, we're going to get this button that will appear, and it'll be Investigate Timing Violation. So let's go ahead and click on it and see what information we can get. Okay, so notice we've got this path requirement, and because we've specified a clock of 200 megahertz, we only have 5 nanoseconds for all that code to finish. Okay, so if we take a look at this, the total delay we have for our code is 9.11. Okay, so it looks like it takes almost twice as long for our code to execute than is required. Okay, so at this particular speed, well, there's several ways to fix the timing error. And the way that we can try fixing it in this particular exercise is we can increase the clock, or we can make the clock run at a slower speed. Okay, so let's go ahead and do a close. And I'm going to close this compilation window as well. And let's go to our block diagram. So in this case, maybe we don't necessarily need this code to execute at a clock rate of 200 megahertz. So we can double click this. And in this exercise, we're just going to choose a slower clock of 80 megahertz. And based on what we saw in that previous timing violations window, we can do some calculations and we can see that our code will definitely fit inside 80 megahertz clock. Okay, so we can take 80 megahertz, click OK. And if I were to run this, I'll just let you know right now that at 80 megahertz, that code will be able to compile. We saw that there was a total delay, I think, of about 9 nanoseconds. So if you do 1 divided by 9 nanoseconds to figure out what your maximum frequency that will compile at, 80 megahertz is well below that. So this should compile. So I'm not going to take the time to compile it here, and you can just take my word for it, or you can do the exercise. Okay, so let's go through these discussion questions real quick. So why is the 9234 analog input FPGA I/O node not supported in a single cycle time loop? So remember, the analog input FPGA I/O node is going to take more than one clock tick to execute. Therefore, it cannot work inside a single cycle time loop. How can you estimate the fastest derived clock rate with the single cycle time loop will successfully compile? So if you remember what we just did in that exercise, we were able to try to compile it at 200 megahertz, right? And it failed. And we went to the timing violation window and we saw how much it failed by. And we saw that the total delay of our code inside there was about 9 nanoseconds. So to find the fastest possible clock rate that our current code could go at, we would take that 9 nanoseconds and we would do 1 divided by 9 nanoseconds to get the frequency, right? So if you did 1 divided by 9 nanoseconds, that would get you something about 111 megahertz. So if you wanted to pick a clock rate that it'll compile at, you can try to do something that's 111 megahertz or slower. Now you can troubleshoot single cycle time loop errors. Next, we will use pipelining to increase the throughput or speed of an FPGA loop. In the previous section, we described troubleshooting single cycle time loop errors. By the end of this module, you will be able to use pipelining to increase the throughput or speed of an FPGA loop. In this section, we'll talk about a technique called pipelining. And this is a technique that you can use to increase the throughput or the speed of an FPGA loop. So what pipelining will do is it takes advantage of parallel processing capabilities of an FPGA. And by taking advantage of this, we're going to increase the efficiency of our code. Okay? So the first thing you need to do for pipelining is you'll need to divide your code into discrete steps. So let's take a look at our block diagram here on the left. So let's say we've got some code and we were able to divide that code up into section A and section B. Okay? So for this example, let's just say section A takes 5 milliseconds to execute and section B also takes 5 milliseconds to execute. Okay? If we look at that example on the left, the total amount of time it's going to take to execute A and B is going to be 10 milliseconds, right? Because they're 5 milliseconds each. One way we can try to optimize this a little bit more and decrease the loop period is we can do pipelining. So if we take a look at the block diagram on the right, that's exactly what we've done. So in this case, we pipelined this. We've separated sections A and section B, and they're now happening in parallel. So on the left, they're happening sequentially, but on the right-hand side, they're happening in parallel, so we can try to optimize it for speed, right? If we take a look at the diagram on the right, we'll have section A. It's going to send an output to the shift register on that first iteration, okay? Now, on the second iteration, what A had sent to the shift register is going to come out of the shift register on the left and feed it into section B, and B will be able to process that code. But at the same time, in parallel, A is already processing the next piece of data. So at this point, if we take a look at the period of this loop, because section A takes 5 milliseconds to execute and section B takes 5 milliseconds to execute, if they're happening in parallel, this entire while loop is actually executing every 5 milliseconds, which is twice as fast as what we had before. And this idea is what describes pipelining. Okay, so we're using pipelining now to increase the throughput and speed of this loop. So in this slide, we're doing the same thing we did on the previous slide, except we're using a feedback node instead. Okay, so a feedback node has the same functionality as a shift register, but just because of the way that it looks, it's able to maintain a more congruous VI appearance. So if we take a look at the code on the left, that's our original sequential code. We can kind of keep that same look and feel, but add the pipelining by inserting a feedback node in between. Okay, so a feedback node, the functionality is the same as a shift register. So on the very first iteration here, we're going to have section A send some data to the feedback node, and then the next iteration of this while loop, the feedback node is going to output the previous value that A had put into it and send it to B. And then at the same time, A is going to be executing in parallel. So it's the exact same behavior that we saw in that previous slide with the shift registers. We just have a different appearance and a different way of showing it by using a feedback node. So let's take a look at a basic example of pipelining inside LabVIEW. So here we've just got some simple code, and if we take a look at it and we kind of count up what's going on, it's going to take 5 cycles for the code to execute and 2 cycles for the loop to execute. Okay, so let's say that input control equals 1 for iteration 0, 1, 2, and 3. Well, the output is going to be 1, 5, 9, and 13. And we have all of those functions happening in sequence. Okay, so let's think about how we could pipeline this and make it a little bit more efficient and increase our rates and throughput. So here we've pipelined the code on the right hand side, and we've done that by using shift registers. So what's happening here is kind of what we described earlier. If we take a look at the code on the right hand side, it's going to have a faster loop rate, and that's because we pipelined it. So the very first iteration, we're going to get our input of 1, we're going to do the multiply, and we're going to send it into our shift register. Okay, the next iteration of the loop, that data is going to come out of that top shift register, and it's going to go inside the scale by power of 2 function and send that result into the next shift register. On the third iteration, that original data from our input is going to propagate down to the bottom shift register, and then that data is going to come out, and then we're going to get our first valid output. Okay, but at the same time, the increment function, the scale by power of 2, and the multiply function are all happening in parallel at the same time. So we're able to decrease the loop period for this loop, which is going to allow us to have faster speeds and more throughput. So if we take a look at that this particular example, it used to take more than 5 clock cycles to execute in our previous example, and by pipelining it, we've been able to make the code inside on the right-hand side only take 3 cycles to execute for the code and an additional 2 for the while loop overhead. Okay, so we've decreased the time that this while loop needs to execute. So if we look at that third bullet now, let's say we have an input of 1 for iterations 0, 1, 2, and 3. Well, if you look at the output, the first 2 outputs are not going to be valid data because the original data has not propagated down to that bottom shift register yet. So you're going to have to wait until the third iteration of this while loop for that first valid output, which is 1 and then 5. So here we take a look at that same example of pipelining that we did in the previous slide, and instead of using shift registers, which kind of makes the code kind of broken up and a little bit hard to read, instead we're going to replace those shift registers with feedback nodes. And this is going to be the exact same functionality, but if you take a look at the code on the right, it's a little bit easier to read and it's easier to kind of see the sequence of the calculations and algorithm here. Okay, so a lot of times you'd want to use feedback nodes instead of shift registers just to make your code a little bit more readable. So here we see another example of pipelining. So let's take a look at the code on the left. So the code on the left is going to be our code that is not pipelined yet. Okay, so if we take a look at what's actually happening, everything is happening sequentially. So first you have the analog input with that FPGA I/O node, and that analog input is going to take a long time. It's going to take 170 ticks. Then you have some other calculations like scaling, and that's going to take another 2 ticks. And then you have your analog output, which is going to take 38 ticks, and then you've got your overhead of your while loop of 2 ticks. So if you take a look at that, that's going to be 212 clock cycles, which is going to be about 5.3 microseconds. Okay? So now let's take a look at the example on the right, where we've actually done some pipelining. Okay? So by looking at the code on the left, we saw that the analog input took a long time, and we could do pretty much the rest of the code at the same time as the analog input. So what we've decided to do is we pipelined it. So you can think of section A of your code of the pipeline is going to be your analog input. And then section B that gets pipelined is everything else. Okay? So notice that we've got our feedback node separating our 2 sections. So we've got a feedback node separating the analog input and the analog output and the scaling functions. So if you take a look at the graphic on the bottom right, we see that our analog input is going to take 170 ticks, but the same time in parallel, we're also doing the scaling and the analog output, which is a total of 40 ticks. So if we take a look at that, we take the longest path, which is the 170 ticks, plus the while loop overhead of 2 ticks, and we've got a total clock cycle of 172, which corresponds to 4.3 microseconds. So by doing pipelining in this case, we made our while loop execute 19% faster. Okay, so let's walk through an example optimization. So what do you do if your diagram executes too slowly? So if we take a look at this example, we see that our code takes 12 cycles to execute. So what's the first thing we can do? Well, we can take a look at our code and we can just try to look at some best practices and replace some of the functions to have the same functionality but use more efficient coding. So let's take a look at the next slide for what we can do. So here we see that we've shortened the longest path by using some basic optimizations. So we've gone from 12 cycles down to 9 cycles. Okay, so what else can we do? On this slide, we've shortened the longest path even further by implementing pipelining. So notice that we've pipelined this, and as a result, we are down to 6 cycles. Okay, so this is just an example of how to do some optimization. First, do some basic optimizations, and then if you need it to be even faster, then you can implement some pipelining. Now you can use pipelining to increase the throughput or speed of an FPGA loop. Next, we will use pipelining to increase the throughput or speed of a single cycle time loop. In the previous section, we used pipelining to increase the throughput or speed of an FPGA loop. By the end of this module, you will be able to use pipelining to increase the throughput or speed of a single cycle time loop. So if we take a look at this slide, we've got a single cycle time loop and we've got some code in there. So notice that we've got a piece of logic over there, and what we can do is we can take that logic and break it up into 2 pieces and then pipeline it. So as you can see in this slide, we are going to try to reduce the total length of the code inside the single cycle time loop by pipelining. So we've taken that logic and we've broken it up into 2 pieces, and the next step we're going to do is pipeline it. So in this slide, we see that we pipelined it and we've taken those 2 pieces and we've used shift registers to implement our pipelining. So this is just the same thing that we talked about before in previous slides. And we could also have implemented this pipelining using feedback nodes instead if we wanted to make the code a little bit more readable. Okay, so let's talk about some caveats with pipelining. So one, it might require your code to be restructured. This is more of a concern if you're using shift registers to implement your pipelining, because you're going to have to move things around, and things, instead of going from left to right, they go from top to bottom. This caveat is greatly reduced by using feedback nodes instead. If you use feedback nodes, as we see at the bottom, we still preserve the left to right kind of readability of our code, but we do gain the advantage of having pipelining. So the other one caveat that I want to talk about is the latency for pipelining. So the latency for a pipeline with n steps, the final output is going to be invalid until the nth iteration. Okay, so let's talk about this a little bit. So if we take a look at the code at the bottom here, let's kind of walk through it. So on the very first iteration, we're going to get an input, and that's going to go to process data. Okay, so the very first iteration process data is going to send data to that first feedback node. Now the second iteration, what happens? Well, that data, that valid data, comes out of the first feedback node and goes to the second process data, and then it travels on and puts it into the second feedback node. Okay, and now on the third iteration, finally we get that valid data out of the second feedback node. It goes into the process data, and the output of process data is our first valid output. And because this is a three-step pipeline, we didn't get valid data until the third iteration. To deal with that, in this particular block diagram, if we take a look at the bottom, we have implemented something where we're looking at the iteration, and we're seeing if it's greater than or equal to 2, which means it's the third iteration of the single cycle time loop already, and then we're going to output a true on the third iteration and later. So in this case, if you look at that case structure, we're only going to output a result from the third iteration and later, because that's the only time when that output will be valid. Okay, so let's do exercise 6.3. And if you're able to at this point, this is a good time to do exercise 6.3 pipelining. For now, I'm just going to give an overview walkthrough through this exercise. Okay, let's take a look at exercise 6.3 pipelining. Okay, so what I'm going to do first is I'm going to open up this VI for pipelining, which is executing on our FPGA. And I'm going to take a look at the block diagram. So if we take a look at this block diagram, right now there's no pipelining going on, right? So in the single cycle time loop, notice that we're trying to make it execute at a clock rate of 80 megahertz. So we've got our input here. It's going to process data. It's going to another process data and another one and the result. So we've got 3 chunks of code right here. Okay, so if I were to hit the run button and try to compile it, this would actually fail, and this code that we have here is not going to be able to fit within one clock cycle of an 80 megahertz clock. Okay, so let me show you a picture, a little screenshot of what the timing violation analysis window would have looked like. So if we take a look at this, notice that over here we've got our path 1. We got a requirement of 12.49 nanoseconds, and that requirement comes from the fact that we want to use an 80 megahertz clock over here. Okay, so that means everything, all the code inside here needs to finish within 12.49 nanoseconds. If we go over here to total delay, notice that the code that we have here takes a total of 27.47 nanoseconds to execute. Just by looking at that, we can see that, okay, that's much greater than 12.49. So what can we do to try to make our code fit within 12.49 nanoseconds? Well, we can examine the timing violation analysis window, and let's take a look at our code here and see how it breaks it down. So if we take a look at that first process data, VI, notice that the total delay here is 8.71. Okay? And if we look at that second process delay, that's going to take 8.79 nanoseconds. And that third process data that we have in our VI is going to take about 8.31 nanoseconds, at least on this compilation. So if we take a look at that, all those process datas are well below 12.49 nanoseconds. So if we were able to pipeline this and we were able to execute those process datas, those 3 in parallel instead of sequentially, then we can actually meet this requirement of 12.49 nanoseconds by a lot. Okay? So let me close this, and let's go to our solution. So this is what we have now that caused that timing violation, because we're executing all these in sequentially. I'm going to close this, and I'm going to go to pipelining solution. So if I was to open this up and do it this way, notice that this is still 80 megahertz, but now I've done some pipelining in here. So I've added this feedback node here and a feedback node here as well. And now we're going to have a result that is pipelined through this algorithm. Okay, so over here, just like we saw in the previous slide, this is just some code to only output a result after that we're going to wait until the third iteration and later to actually output a valid result. Now you can use pipelining to increase the throughput or speed of a single cycle time loop. Next, we will define fixed point data type terminology.